One of the first applications we'd like to discuss today is that of ESD, electrostatic discharge in space. The idea is that when we are in orbit or beyond, traveling to the moon, for example, or to another planet, we are exposed to a lot of radiation environments. One of the key radiation environment that we want to look at is that of electrons and ions of high energy that can penetrate inside a component and charge a dielectric, for example. Think of the solar array of a satellite and the dielectrics present there being at risk of charging up due to deep dielectric charging. One of the ways we can mitigate this is by adding some shielding, for example, or we can also change the materials that we're using to be able to dissipate that charge that builds up in the system, or we can work on the component geometry and design to make sure we can minimize electromagnetic fields that are building up inside the system. In Ansys Charge Plus, we have the ability to model how that radiation interacts with the bulk matter and the materials and the components and solve for the fields in 3D. It is a very novel technology in its ability to connect full wave electromagnetics with radiation transport. One of the things we really want to focus on is modeling these high energy electrons and their proper energy, typically in the MEV region, and how they deposit inside the solar cell. And so this is an example here in our case study of a dielectric solar cell coupon with 4 cells, each with a bias voltage of about 10 volt difference between each cell, and they're embedded in a glass dielectric protection layer. The electrons are going to penetrate inside the glass and deposit charge inside the system. And if that charge becomes too much, the fields inside the glass are going to be very high and could exceed the dielectric strength of the glass. This can happen when we're talking about very dielectric heavy materials. For example, the Lucy spacecraft has that solar cell that is very heavy in terms of dielectrics and is very sensitive to the amount of radiation that is present. And so depending on the type of environment that you're exposed to, if you're, for example, in low Earth orbit or in GEO, the response and the amount of charging inside the cell is going to be very different. What we're trying to mitigate is the risk of damaging the solar cell and destroying the solar cell. The consequences are drastic. If you actually get an ESD inside the solar cell, you're going to completely destroy the mission and lose the whole satellite. One of the results that we can provide with Ansys Charge Plus is the electromagnetic fields that are building up inside the system, but we can also model the ESD itself and how much energy is present inside the discharge. Where is the discharge happening inside the solar cell and how much of the material is getting damaged? All these information can tell you if you're at risk of extensive damage and full mission failure, or if you're actually able to accommodate some level of charging based on the environment that you're exposed to. In this animation that we're presenting, in these results, we are showing the electromagnetic fields that are dissipating as the material is changing conductivity when the discharge is propagating through the glass. So we're able to see that the charge is floating from the top of the glass to the bottom of the solar cell, which is a conductive backing. From this ESD simulation, you can see how susceptible solar arrays are to space environment effects. Solar arrays are critical to power sensitive equipments for long periods of time across your whole mission. With Ansys Charge Plus, you can assess and manage the risk of ESD and prevent catastrophic failures.